The next thing is the BD process moves from its state k to k minus 1 if a death occur. Now currently, for example, earlier we suppose k is the total number in population which is represented by, which is also known as state value. If there is a total, if in at any particular locality the total population is k, then if a death occurs, it means k goes to k minus 1. So now the current state is k minus 1. Similarly, if the state is k and state to it goes to state k plus 1 if a birth occur. It means whenever a birth occur in a population, then it adds. So the particular state, it stays in the same. So the particular system stays in the state k plus 1 now whenever the birth occurs. If no birth, if no birth or death occurs, then it remains unchanged. So the state, or we can say that population, remains unchanged. So whenever a death occurs, then if the population is k, then it goes to k minus 1, or we can say that the state k goes to k minus 1. If birth occurs, then the population or state k goes to state k plus 1 or population k plus 1. If no birth, if no birth or death occurs, if no birth or no death occurs, it means it remains no change state. Earlier the state is k and now also the state is k. So this is the particular fundamental behavior or process, the fundamental work behavior of the PD process, birth death process, during time period under consideration. So these things, or we can say that these state transition goes under some time period under consideration. This behavior of the particular birth death process, we can make we can draw a particular figure for this regarding state transition of a birth death process. Let at time t there are three possibility. First, the state is k plus 1. Second one, the state is k. And third one, the state is k minus 1. We are drawing a particular figure to understand the particular state transition of birth death process, in which we mentioned here at time t there are three state k plus 1, k and k minus 1. A particular time period, or we can say that the observation period, which is del t. So after time del t, it means at time t plus del t, if there is a single state k. At time t there are three states k plus 1, k and k minus 1. After del t time duration, it means after del t time duration the time is t plus del t. It means at time t plus del t there is a single state, that is k. So when, earlier if at time t the particular state is k plus 1, after time del t, if the state goes from state k plus 1 to state k, it means it means there is there is a loss of 1, k plus 1 to k. So it means here death occurs, single death occurs. If earlier at time t the state is k and after time del t the state is again k, it means there is no change. It means no death or no birth occurs. If at time t the state value or the population is k minus 1 and after time del t the state is k or the population is k, then it means there is a birth occur. So this is the state transitions of a birth death process. So it is a state transition of a birth death process. So a telecommunication network, therefore, a telecommunication network can be modeled as BD process, where the number of busy servers represent population. It means where the k represent the number of busy servers, or we can say that the population. A call request means birth related to call request. Death means call termination. So there is so how so this way a telecommunication network can be modeled as BD process, where k is the number of busy servers, birth is means call request, death means call termination. To analyze, now we analyze this birth death process. To analyze this birth death process, first of all, we assume that the particular time period del t, the observation time period, which is del t. So let the particular time interval del t is very small. There can almost be only one state transition can occur. So first our assumption is that the time del t, the observation time del t, time consideration del t should be very small. So only one state transition can take place, either one single birth, either single death, or no change. And we further assume that we can further assume that our next assumption is that the probability of an arrival or termination in a particular interval is independent of what had happened in earlier time intervals. The probability of an arrival further assume that the probability of an arrival is directly proportional to the time interval del t. So our further assumption is that the probability of an arrival or termination in a particular interval is independent of what had happened in earlier time intervals, or the probability of an arrival is directly proportional to the time interval del t. So these are the assumptions we are we are taking for find out or determine the dynamics of a switching system. Now our next step, determine the dynamics of a switching system. Determine the dynamics of a switching system. To determine the dynamics of a switching system modeled as BD process, first of all, let PKT equals to the probability that the system is in state K at time t. So first we assume that PKT, which represented as the probability that the system is in state K at time t. Next, lambda K, which is called arrival rate in state K. And third is mu K, which is called termination rate in state K. So there are three particular assumptions, that is a PKT, which represent the probability that the system is in state K at time. The system is in state K at time t. Second one is lambda K, lambda representing calling arrival rate. K represent what is the state. So at particular state K, the particular call arrival rate, which is represented by lambda K. Similarly, the call termination rate represented by mu, and the state is K. So at state K, the particular call termination rate is mu K. Then we have the probability in the time interval del t. It means these are after time del t. What are the particular probabilities? So at in the time interval del t, it means after time del t, what are the probabilities? So the probability of exactly one arrival, it equals to lambda del t. Second one is probability of